You ever see a headline that makes some wild connection and you just kind of nod and accept it? Well, we are swimming in data that seems to tell us a clear story. But the thing is, sometimes that story is completely wrong. Today, we're going to put on our detective hats and figure out how we get so easily fooled and, more importantly, how we can find the truth. All right, let's open our first case file. This one's a real-life medical mystery. For years, doctors noticed this really striking pattern. Women who were taking something called hormone replacement therapy, or HRT, seemed to have way lower rates of heart disease. I mean, the data was so consistent, it really looked like a miracle cure.
But then scientists decided to put it to the ultimate test with these super rigorous randomized controlled trials. And the results? They were absolutely shocking. The therapy didn't help at all. In fact, it actually increased the risk of heart disease, even if just by a little bit. So you've got this mountain of observational data saying one thing, and the scientific gold standard saying the complete opposite. What gives?
And that right there is the central question for us today. How could so many different studies, looking at thousands and thousands of women, get this story so incredibly backwards? The answer is one of the single most important ideas in all of statistics.
The whole mystery, it turns out, came down to a really simple, really common mental trap, confusing a correlation, two things happening together, with causation, one thing actually causing the other. This is rule number one for any data detective. Say it with me. Correlation does not imply causation. There's even a fancy Latin name for this mistake, cum hoc ergo propter hoc, which basically means with this, therefore because of this. To crack our HRT case, we have to understand why this rule gets broken all the time. So, let's meet the usual suspect.
Okay, time for a police lineup. We're going to look at the three most wanted culprits that trick our brains into seeing cause and effect, where there's nothing there at all.
First up, we have suspect number one, reverse causation. This is the classic, whoops, got it completely backwards mistake. It's when we see that A and B are linked, but we think A causes B, when really, B is causing A. For instance, you could notice that the faster windmills spin, the windier it gets. The correlation is perfect. But obviously, saying the windmills are causing the wind is, well, it's just silly, right? The wind is causing the windmills to spin. Now, it seems super obvious here, but trust me, this exact mistake happens all the time in much more complicated ways.
Okay, on to our second suspect. This one is probably the most common culprit of them all. Statisticians call it a confounding variable, but I like to call it the hidden accomplice. It's some secret third factor, lurking in the shadows, pulling all the strings, and making two totally unrelated things look like they're connected.
Here's a funny one for you. There is a strong statistical correlation between sleeping with your shoes on and waking up with a headache. So does shoes cause headaches? Probably not. The hidden accomplice here is a third thing, like, say, going to bed drunk, which is probably the real reason for both the shoes and the headache. And here's the classic example. Ice cream sales are almost perfectly correlated with the number of drowning deaths. So does eating ice cream make you drown? Of course not. The hidden accomplice is hot weather. When it's hot, people buy more ice cream and they go swimming more often. And this is exactly what happened in our HRT mystery. It turned out the women taking HRT were, on average, from higher socioeconomic groups. That meant they also had better diets, exercised more, and had better healthcare in general. That healthier lifestyle was the hidden accomplice. That was the real reason for their lower heart disease rates, not the HRT at all. All right, our last suspect is the weirdest one, the one that can really mess with your head. It's just pure random chance. Sometimes two things are correlated for a while with absolutely zero connection. It's a total statistical fluke.
Get this. For more than 60 years, from 1936 all the way to 2000, this one bizarre rule held true. If the Washington Redskins football team won their last home game before the presidential election, the party already in the White House would win. If they lost, the incumbent party would lose. It's a perfect example of what's called a spurious correlation. There's no hidden accomplice, no logical reason, just a really, really long and strange coincidence that, of course, eventually broke. So wow, we've got reverse causation, hidden accomplices, and just plain old coincidence. With all these traps, how do scientists ever figure out what's really causing what? Well, they have a very powerful tool in their detective kit that lets them combine all the clues. It's called a meta-analysis, and you can think of it as doing research about other research.
Instead of just looking at one study, scientists gather up all the studies ever done on a topic and use some clever statistics to merge their results. This gives them a huge amount of data and helps them see the big picture, the whole forest, instead of just one or two trees.
And it's a really thorough process. First, they search for every study they can find. Then, they filter them, only keeping the ones that meet a high standard of quality. Finally, they calculate a weighted average of all the results, giving more oomph to the bigger, more reliable studies. It sounds like the perfect tool, right? But it has one big, secret weakness.
And that brings us to the final twist in our detective story. It's a type of bias that can corrupt the evidence before a detective even gets to the scene.
You see, a meta-analysis is only as good as the research it includes. So, what happens if some of the clues, some of the studies, never even see the light of day? This is something called publication bias, or my favorite name for it, the file drawer problem. Think about it. Journals are way more likely to publish a study with an exciting, positive result than a boring study where nothing happened. So those studies with negative or no results, they often just get shoved into a researcher's file drawer and no one ever hears about them. And this creates a massively skewed view of the truth, making an effect look much bigger than it really is.
Scientists actually have a cool visual tool to check for this. It's called a funnel plot. The one on the left here is what you want to see. It's healthy. You've got studies scattered nicely and symmetrically on both sides of the average. But now look at the one on the right. See that big gap at the bottom? That suggests that a bunch of studies with negative results are missing. They're stuck in that file drawer, giving us a really lopsided and misleading picture of reality.
Okay, now that we've seen how easy it is to be fooled and the tools scientists use to fight back, let's wrap this all up by giving you your very own data detective toolkit. This is what you can use to think more critically next time a big claim comes across your screen.
So the next time you see a headline linking A and B, just pause and run through this checklist in your head. 1. Could it actually be the other way around? 2. Is there a hidden accomplice, a C, that's causing both A and B? 3. Could this just be a total fluke, a random coincidence? And 4. Are we really seeing all the evidence, or are the boring studies stuck in the file drawer?
Now, this doesn't mean we should just ignore correlations. As the great data expert Edward Tufte has said, it's not causation, but it sure is a hint. A correlation is a clue. It's the breadcrumb trail that often leads a good detective to start an investigation and find out what's really going on.
So remember, being a good data detective isn't about having all the answers. It's about knowing the right questions to ask. A correlation is where the mystery begins, not where it ends.